Hey kiddos, and welcome to 14.2, the second installment of our understanding of standard cells and cell potentials. This time what we're going to do is we're going to learn how to calculate cell potential, and we're going to take a look at what that looks like in our data booklet. So there are numbers associated with those reduction half reactions all the way to your right, and we're just going to learn how to read those. So a standard cell is a voltaic cell in which each half cell contains all entities shown in the half reaction equation at SATP with a concentration of 1.0 moles per liter for the aqueous solution. So that's basically where the standard cell, the conditions is that the reaction is happening at 1.0 moles per liter in SATP. So nothing really there, just giving you some background information. The standard cell potential is the maximum electric potential difference or the voltage of the cell operating under these standard conditions. So at SATP, this is what's going on with the potentials. Okay, so you need to memorize how to find the cell potential, and that's basically using your cell potential for each of the reduction half reactions at the cathode and the anode. This needs to be memorized. Remember, a voltaic cell is a combination of two half cells, one at the anode and one that occurs at the cathode. So let's take a look at what this looks like. If you take a look at your data booklet, you'll find a table of the half reactions, which you've been working with, no big deal. But what you haven't noticed maybe, or maybe you've noticed but you're like, oh, what are these for? We haven't used these before, is your electric potential, your electrical potential. And that's basically measured in volts. And it's all these numbers over here. Now notice that these numbers are in some kind of sequence, right? They go lower, the numbers decrease as we move down the list. This is your strongest electrical potential, and it goes down from there. And if you take a look at that, you can kind of go, oh, look at that. This is also your strongest oxidizing agent, moving down to your far, just for this right here, that would be your strongest reducing agent. So basically, the reduction half reactions that make up redox table in the data book are listed in order of decreasing standard reduction potential. And remember, the units for that are volts. And this happens at 1.0 moles per liter solutions at SATP. Remember, SATP is at 25 degrees Celsius and a pressure of 101.325 kilopascals. And those are your standard conditions. That's just some background info, no big deal there. So the value of the reduction potential represents the ability. So what do these numbers represent? What's the point of this? It represents the ability of a half cell to attract electrons. So that's kind of cool. Or what it does is it gives you a value when we're talking about the strength of the oxidizing agent. So it makes sense that if your SOA is top left, then this number here has to be the highest. So that makes sense. The half cell with the higher reduction potential will attract electrons from the half cell with the lower reduction potential. That makes sense as well. So let's take a look at the standard hydrogen half cell. It is impossible to determine experimentally the reduction potential of a single half cell because you need to have two half cells for a redox reaction to occur. So basically, what has happened is they just chose, like some chemists were sitting around, they went to a restaurant and they're like, you know what guys, we need to compare everything to something so that we can start giving out numbers. So they decided that the hydrogen half cell was the one to be chosen as the reference cell. So every cell is compared to the hydrogen half cell. Now here's the thing, kiddos, the redox table that you have, it's certainly not complete. That's just a snippet of all the data, but obviously we'll only use the information from that table to have you guys think about questions, right? So they arbitrarily decided that the hydrogen half cell is going to be your reference cell. So every cell is going to be compared to this. And they gave it a value of 0. So if anything is stronger, right, if it has higher voltage, or what we decided was like if it has stronger oxidizing agents to attract those electrons, the number will be higher. If it's lower, if it's not so much of a transfer of electrons, it's kind of weak, it's going to have a negative value. But they decided, what we get all of this is that hydrogen is the half reaction that we're going to be taking a look at. Note that the choice of this half reaction has a voltage of 0, and that's completely arbitrary. What that means is that was just decided. That isn't the case because all of the data collected told us that it was 0. Someone just said, hey, we'll assign this 0 volts, and we'll compare everything to that cell. So really, why do we care? And what kind of questions can be generated from this? So here's an example of a question. And I'll show you how to break it down and how to find the answer, right? Because you do get these types of questions. Scientists Tom and Janelle rewrite the reduction table in the data booklet. They choose the half reaction, this half reaction, okay, to be the new reference point or the new reference cell. So what they're saying is instead of hydrogen being the reference cell and having a voltage of 0, they're choosing this half reaction to be the reference cell. So this half reaction is going to have a voltage of 0. Based on this new reference point, choose the true statement. So then what you might get is you might get a series of half reactions with voltages that do not match the voltages in your data booklet because this time the reference cell has changed. So how do we figure this out? What do we do? Okay, so let's take a look at the information from your redox table. This would be the new reference point, right? So instead of hydrogen, it's this one, and this is its previous potential, right? 0.54 voltage of 0.54. So now this becomes 0.00, okay? And it doesn't matter, it's positive 0.00 volts. So we have to shift everything. So what did we do to this number to get to a voltage of 0, right? If the new reference cell, and here it is, this is the original, changed to 0. What happened to make that change? Well, we start off with the positive 0.54. We needed to add a negative 0.54 to get it to a potential difference of 0. So what you have to do is you have to do this, okay, to all of the entities, to all of the half reactions, which gives, I guess, leads us to lead, which had an original cell potential of negative 0.13. Now we have to add a negative 0.54, because that's what we did to this to make it to 0. And you get a new cell potential of negative 0.67 volts. Okay, that's how you do it. That's what happens. It's not so bad. So measuring standard potentials for reduction half reactions. To measure the reduction potential of a half cell, construct a standard cell with the hydrogen reference half cell. The cell potential is measured with a voltmeter. If the cell potential is positive, then the positive terminal in the voltmeter is connected to the cathode, and the oxidizing agent at the cathode is stronger than the hydrogen ions. So a positive cell potential, right? So if the potential is greater than 0, indicates that the net reaction is spontaneous. Okay? And this is indicative of all voltaic cells. All voltaic cells are going to have a positive cell potential. Okay, that is something that you have to put in the vault. To analyze a standard cell, you must determine which electrode is the cathode and which is the anode, which you already know how to do because you just look for your SOA and your SRA, and you basically use this formula. You have to just basically take your cell potential reduction half reaction at the cathode and at the anode and subtract the cathode from the anode. Here's an example. A standard lead dichromate cell is constructed. Write the cell notation, label the electrodes, and calculate the standard cell potential. So what you have to do is you have to differentiate where the cathode is and where the anode is. It's cathode subtract anode. All you need to do is once you have these half reactions, look them up in your, actually this is going to be, this is an inert electrode. So you have to look at your electrolyte to figure out if it's an SOA or an SRA. And we know that this is your anode, right? You search out your half reactions on your data booklet and just basically look up the cell potentials, and it's your cathode, subtract your anode, and that's going to give you a cell potential of positive 1.36 volts. So it's larger than 0. It's spontaneous. What does that mean? It's going to produce electrons, right? And it's a voltaic cell because it does generate electrons. A standard scandium copper cell is constructed and the cell potential measured. The voltmeter indicates that the copper electrode is positive. And we have the net, right? The total, and it's a positive 2.36 volts, which means that it's spontaneous. And it also means that it's a voltaic cell. Okay, cool. Write and label the half reaction and net reactions and calculate the standard reduction potential of the scandium ion. That's what you're looking for here. So something that's really important, remember, we need to use these coefficients to balance our equation. But now, just because I'm multiplying the 3 times all of this, because it's like a distributive property, right? We do not multiply the potential by 3. Do not multiply by the coefficient. Just leave the number on its own. So basically what we know the cell potential, we're just looking for the half reaction of the scandium, okay? So basically all you have to do is rearrange your formula or use your algebra to get an answer of negative 2.02 volts. So rules for analyzing standard cells. I'm sorry, I'm going to read this to you. Determine which electrode is the cathode. And let's review. A cathode is the electrode where the strongest oxidizing agent, your SOA, present in the cell reacts. And to review, the OA is the closest to the top on the left-hand side of the redox table. The very highest is your SOA. If required, copy the reduction half reaction for the strongest oxidizing agent and its reduction potential. Then what you have to do is determine which electrode is the anode. So obviously, if you figured out the cathode, the other electrode is going to be your anode. The anode is the electrode where the strongest reducing agent present in the cell reacts, right? So this is your SRA. The RA that is closest to the bottom on the right happens to be your SRA, which you know. If required, copy the oxidation half reaction. Remember, you reverse the half reaction so that you can cancel out your electrons. Determine the overall cell reaction, cathode minus anode. Balance the electrons for the two half reactions, but do not change the potential. And add the half reaction equations. Thus, determine the standard cell potential using the equation, your cathode subtract your anode. If this answer is positive, it's a voltaic cell, it's spontaneous. If the answer is negative or less than 0, it is non-spontaneous and it's not a voltaic cell, which is kind of a little bit of foreshadowing of what's to come. Method of sketching and labeling cells. Let's review. List the entities. Determine your SOA and your SRA. Write the half and net reactions with voltages. You draw your cell. And then label your cathode anode, right? Label what's positive and negative. Label the flow of electrons. And determine the ion flow and include your electrolytes. If you do all of these things, you are golden. So there's some homework, but I am posting some practice. So now we're going to get through a few definitions Not a big deal, just some definitions. Corrosion is the electrochemical process in which a metal is oxidized. So corrosion, you have an oxidization of your metal. An example is a lot of metals rust because of the reaction with oxygen in the air. By substances in the environment returning the metal to an ore-like state. In general, any metal appearing below the various oxygen half reactions in a redox table will be oxidized in our environment, so very interesting. A rusting of iron, here we have at the cathode, at the anode, there is our net reaction. The iron 2 hydroxide precipitate is further oxidized to eventually form rust. So rust is all about chem. So the rusting of iron requires the presence of oxygen and water and is accelerated by the presence of acidic solutions, electrolytes, mechanical stresses, and contact with less active metals. Corrosion prevention. So how do we prevent this corrosion from happening? There's a few things that we could do. First thing we can do is we can add a protective coating. Paint and other metals such as tin and zinc are most commonly used. We coat things like iron with other metals to just basically keep the iron from corroding. Tin adheres well to the surface of iron, and the outer surface of the tin coating has a thin, strongly adhering layer of tin oxide that protects the tin. Iron has been galvanized when it has been coated with a layer of zinc, so we called it galvanized iron when it has coated with zinc. Zinc is a stronger reducing agent than iron, thus more easily oxidized. So the zinc is going to be oxidized before the iron, which really what it does is protecting the iron. So here's an example. Zinc is oxidized instead of the iron. It is protecting, so the zinc will break down and the iron is good to go. It'll be fine. Another way we can protect our metals is cathodic protection. Recall the oxidation or loss of electrons takes place at the anode of a voltaic cell. Cathodic protection is when the iron is forced to become the cathode by supplying the iron with electrons. Impressed current cathodic protection. An impressed current is an electric current forced to flow toward an iron object by an external potential difference, which is provided by a constant power supply. This is commonly used for pipelines in order to protect the metal that the oil is going through. Here's another example, sacrificial anode. A sacrificial anode is a metal that is more easily oxidized than iron and connected to the iron object to be protected. The water pipe is turned into the cathode and magnesium is used as a sacrificial anode. So the magnesium itself is going to break down, okay, which allows the metal, the iron, to stay safe. I guess safe is kind of an interesting word. Okay, that's it, kiddos. I'm posting some practice. You guys have a great day.